Hello learners, I am Dr. R.B. Malati, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, Bhilai. I welcome you all again to the course Essentials of Surveying, Application and Techniques. In today's lecture, let us look into chain surveying. Chain surveying is an old tool in surveyor's toolkit. Imagine you are using a piece of string or a chain to measure distance directly on the ground, and instead of using complex tools to measure angles, you are relying on the length of the sides of the triangle to get your data. That is chain surveying in a nutshell. It is simple yet remarkably accurate and one of the most straightforward methods for measuring lands. So, here a question for you. Why do we need land surveying in the first place? Well, there are several key reasons. First, the land surveys help to define the exact boundaries of a plot of land. Think of it like marking the edges of your property, so you know exactly where it begins and ends. Next, if you need to know how big a plot of land is, a survey will provide the precise area measurements, which is important for everything from buying to selling land. Next, the third key point is surveys create detailed plans of land plots. Whether you are laying out a new factory or designing a park, a precise plan is essential. Next, boundary demarcation. Sometimes land has already been surveyed, but boundaries need to be re-established, and this survey ensures that boundaries are marked accurately. Next, land division. If you are dividing a larger plot into smaller units, land surveys help to do this so accurately. Lastly, land surveys are vital for engineering projects like aligning roads, railway lines or canals. They provide the necessary data to execute these projects efficiently. So, having understood the importance of land surveying, now the next question is, what are the situations where this chain surveying can be made a suitable choice? First is flat and open ground. Imagine surveying a large flat field with few obstacles. Chain surveying is perfect for such environments where the land is even and open. Large scale plans, that is when you are working on large scale project like mapping out a factory site, chain surveying can be quite effective, especially when the area is not too complex. Third, small areas. For smaller plots of land, chain surveying is ideal because it is quick and straightforward. Yes, these are the suitable areas where chain surveying is done. Now comes the next question. What are those unsuitable areas? Yes, however, chain surveying has its limitation. Large areas, that means for vast expanse of land, chain surveying might not be practical. It becomes cumbersome and less efficient as the area grows. Next, if the land is filled with lot of details like buildings, trees and other structure, chain surveying may be difficult. It is best for simple terrains. Third, for areas with lots of hills and valleys, chain surveying is less effective. The undulating ground can make it challenging to get accurate measurements. So, the bottom line here is, while chain surveying is a good choice for many situations, it is important to know when it is a right tool for the job and when you might need a right approach. So, with this background, let us now see principle of chain surveying and how it works. The core principle as discussed in the last class is, think of chain surveying like putting together a big flat jigsaw puzzle. The basic idea is to break down the area into bunch of triangles. And why triangles? Because triangle is the simplest shape you can work with when it comes to plotting land accurately. If you know the lengths of all three sides of the triangle, you can plot it on a map without needing to worry about angles. This is why chain surveying relies on creating a network of triangles to cover the area. So, what should be the shape, size and arrangement of these triangles? In chain surveying, all the three sides of the triangles are liable to error. So, perfectly shaped triangles come as our first option, that is equilateral triangles. These are like the gold standard. Imagine a triangle where all three sides are the same length and all three angles are 60 degrees. It is the easiest to work with and the most accurate to plot. The errors in measurement and plotting are minimal with these triangles. Next, we have well-conditioned triangles. That is, sometimes you can't always get perfect equilateral triangles. In that case, aim for triangles that are nearly equivalent. These should have angles that are not less than 30 degrees and not more than 120 degrees. These triangles are still pretty good for accurate surveying. And avoiding ill-conditioned triangle. What's the problem with ill-conditioned triangle? These are triangles where the angles are either smaller than 30 degrees or larger than 120 degrees. They are tricky because they can introduce more errors in measurement and plotting. You will need to be extra careful while measuring and plotting. Now, moving to the size, which is the second important thing. If you are surveying a large open field with few obstacles, you can use larger triangles. It is like working on a big canvas where you don't need to worry about fine details. And on the other hand, if you are dealing with an area full of details like a busy city block with lots of buildings and roads, you will want to use smaller triangles. They help in capturing more precise details in a crowded space. Finally, arranging the triangles. The way you arrange these triangles depends on several factors. First is shape and topography. That is, the natural shape and features of the land will influence how you set up your triangles. For instance, if you are working on a hillside, you will need to arrange your triangles to match the slope and elevation changes. Next is obstacles. Any obstacles, whether natural like trees and rocks or artificial like fences and buildings, will affect how you arrange your triangles. You might need to adjust your setup to navigate around these obstacles effectively. So, to sum up here, the principle of chain surveying is all about dividing the land into triangles that are easy to measure and plot. And by focusing on well-shaped, well-sized triangles and by considering the terrain and obstacles, you can ensure accurate and reliable surveying. Let us now understand the key terms in chain surveying. First is main survey station. Think of a main survey station like the corner of a room. It is where two sides of a main triangle come together. In a survey, these points are important because they anchor the main survey lines. For example, if you are surveying a field, the points where your main survey lines meet are called main survey stations. In a diagram, these could be plotted as points A, B, C and D. Next, subsidiary survey station, which is also called tie station. Now you imagine you need to measure a bit more detail inside your main triangle, like adding furniture in a room. The subsidiary stations are the points you need to run additional lines inside the main survey lines. For example, if you need to measure details between points A and B, but you also want extra precision inside the triangle, you might use points E and F as subsidiary survey stations. Next is the main survey lines. These are like the main walls of a room. They are the longest and most important lines that join the main survey station. In your survey, if you have lines connecting points A to B, B to C, C to D and D to A, these are your main survey lines. And therefore, we have auxiliary, subsidiary or tie lines. Imagine these lines as the smaller partitions within the room that help you to get a better layout. They connect the subsidiary survey station and help locate details inside the main area. For example, if you have lines connecting points E to B and F to D, these are your auxiliary or tie lines. They help to pinpoint specific details that are away from the main survey lines. Next, we have baseline. This is the longest line of your main survey lines, like the longest wall in a room. It is essential because all other survey stations are plotted based on this line. For example, if AC is the longest line in your survey, it is called the baseline. Everything else in your survey is referred from this line. And next, the check line. Think of check line like double checking your work. They are run to ensure that the measurements and the layouts are accurate. If the length of the check line matches what you have plotted on your map, your survey is likely accurate. For example, if you have lines HG and MN running through your survey areas, these serve as check lines to confirm everything is correct. So, putting it all together in a survey layout, we have baseline AC, main surveying lines AB, BC, CD and AD, subsidiary or tie lines B and FD, check lines HG and MN, main surveying station A, B, C and D and subsidiary stations E and F. These terms and lines form the backbone of the chain surveying, helping you to measure and map out land with accuracy and efficiency. And by understanding these terms and how they fit together, you can effectively set up and execute a chain surveying. So, let us now understand selecting the survey station and measuring the baselines. When you are out in the field doing chain surveying, making the right choices about where to place your survey stations and how to measure your baseline is important for accurate results. Let us understand the essential points for selecting the stations, measuring baselines and understanding offsets in a way that is quite easy to understand. So, here is a handy guide to select the best survey station. First come the visibility between main station. It means, imagine you are setting up a survey for a large park. You place your main survey station at the corners of the park. To make sure your measurements are accurate, these stations need to be visible from each other. If you can't see one station from another, it is like trying to play a game of hide and seek without knowing where everyone is. Minimize survey lines. It means if you are surveying a plot of land, you should keep your survey lines as short as possible. Next, work from the whole to the part. It means start by measuring the overall shape of the land, then work on the smaller details. It is like taking a wide angle photo first and then zooming it for close-ups. Then form well-conditioned triangles. It means your survey triangles should be as close to equilateral as possible, like making sure your triangles are well balanced. Avoid triangles that are too skinny or too flat as they can introduce errors. Next, include a check line, meaning think of a check line as a safety net. If you have a triangle, add a check line to ensure that everything lines up correctly. Next, use tie lines to avoid long offset, meaning if you need to measure details far from your main survey lines, tie lines act like additional reference points to keep everything accurate, like adding more checkpoints on a long journey. Next is avoid obstacles, meaning if there are trees or buildings in the way, they can make surveying difficult. So, try to choose stations where you can avoid these obstacles, much like choosing a clear path for a straight walk. Next is align with boundaries and roads, means place your largest triangles parallel to existing boundaries or roads to reduce the length of your offsets. This helps keep things straightforward, like making sure your measurements are aligned with the edges of a map. Next, prefer level ground. It means survey lines work best on flat terrain. It is like trying to draw straight lines on a smooth surface rather than on a hilly one. Next, stay clear of traffic. It means if you are surveying along a busy road, position your lines on one side to avoid interruption from traffic. So, having understood the handy guide to select the best survey station, let us look into the selection and measurement of the baseline. So, selection and measurement of the baseline. The baseline is the backbone of your survey. So, getting it right is important. The following points are kept in view while selecting and measuring a baseline. First, it should be laid preferably on a level ground. Next, it should run through the center of the length of the area. It means lay your baseline through the middle of the surveyed area. Third, it should be measured twice or thrice and the mean value accepted as its correct length. Fourth, great care should be taken to ensure straightness of the baseline while measuring. And at the fifth, two baselines perpendicularly bisecting each other should be laid out. It means if your survey is large, laying out two baselines that cross at right angles can provide even more accuracy, like creating a grid to map out a large area. Hope the selection and measurement of the baseline is clear now. So, let us now look about the offsets. In chain surveying, the positions of details, that is boundaries, culverts, roads, streams, bends, etc. are located with respect to the chain line by measuring their distance right or left of the chain line. Such lateral measurements are called offsets. There are two types of offsets, that is perpendicular offsets and oblique offsets. Let us describe each. Perpendicular offsets, it means if you are measuring the distance from a chain line to a building directly, that is a perpendicular offset. It is like measuring the straight line from the edge of a table to the wall. In the figure, EN is a perpendicular offset on the right side of the chain line AB. Next is the oblique offset. Means if you measure the distance at an angle, like from a chain line to a fence at a diagonal, that is a oblique offset. CM and DM are oblique offsets on the right side of the chain line AB. We also have short and long offsets. So, the difference between them is short offsets are quick and easy to measure, like measuring a small distance with a tape measure, and long offsets might be trickier and need careful measurements, like measuring the length of a long piece of wood. Let us understand the measurement of perpendicular offset bit more. When you are offering an offset, you have two key measurements to see. First is the distance along the chain line. This is basically how far along your chain line you have gone from your starting point to the foot of the offset. We call this the chainage. Think of it as your starting station's way of keeping track of how far you have travelled. Next, the length of the offset. This is the distance from the foot of the offset where it meets the chain line to the actual detail point you are interested in. We just call this the length of the offset. Now, picture this with me. In our diagram, AB is your chain line and CP is a perpendicular offset to the left. The distance AC is what we call the chainage of the offset and CP is the length of the offset. And for short offsets, you can usually eyeball the perpendicular direction, but when you are dealing with longer offsets and you need better accuracy, you will want to use tools like an optical square or a cross staff to set out those right angles. So, a quick tip here is try avoiding long offset whenever you can. They can introduce more errors because of tape length inaccuracies or direction mistakes. Plus, short offsets are quicker and more accurate to measure. Let us now talk about oblique offset. This one is important when you need to locate details that are far from your chain line or when you are dealing with critical points like the corners of the buildings are boundary pillars. So why this oblique offset is important? When you want to get the exact position of a detail point, you will take two oblique offset. Think of it like drawing two arcs to pinpoint the location. For example, if you are surveying a building corner, let us call it as H, and you might take oblique offset from points C and D along your chain line AB. This helps you accurately mark where the corner is. Similarly, if you need to check the accuracy of a perpendicular offset you took, say to locate a tree at a point T, you can take oblique offsets from two different points E and G along the chain lines to cross check your measurements. This helps ensure a perpendicular offset from F to T is spot on. I will insist this part again. Imagine in the figure you have got your chain line AB. You take oblique offsets from C and T to locate the building corner H. For the tree at T, you use E and G to double check your perpendicular offsets from F. That's it. Now, let us learn taking offsets. If you don't have an optical square or a cross staff handy, you can still take an offset, and here is how it is done. First is the positioning. Here, the leader, and that is you holding the 0 end of the tape, stands at a point P where you want to take the offset. The follower, your friend, swings the tape in a short arc around point P. Next, finding the foot. The follower looks for the smallest reading on the tape. This is the spot, the foot of the perpendicular from P to the chain line AB. This type of offset is called a swing offset. Next, marking the spot. The follower then fixes an arrow at the spot found. Let us call it as point F and notes the chain edge and the length of the offset. The surveyor double checks everything and records it in the field book. Fourth is arc intersection. To refine it, the leader holds the 0 end at P again, and the follower swings the tape to cut the chain at points E and G, intersecting the chain line at 2 points. The midpoint of E and G is F, the foot of the offset. So now, how many offsets should you take? And it depends on the detail points and the accuracy you actually need. So the good rules here are: take as many offsets as needed to define the outline of the object clearly and accurately. So offsets are essential for every change in the alignment of the detail, and here are some specifics for different types of details. If it is for circular details, yes, that is for round objects, take an offset to the center and measure the radius. For hexagonal or orthogonal shape, take offsets to the ends of the sides nearest to the chain line and measure the lengths. And for straight lines like roads or boundaries, take offsets at each end or change points. For longer straight details, add a few more offsets at intervals to check the accuracy. For irregular boundaries, break them into straight segments and take enough offsets to accurately locate their position. So the bottom line here for this is, taking offsets is all about precision and careful measurement. Whether you are dealing with circles, polygons, straight lines or irregular shape, make sure to capture every detail accurately. Let us understand the degree of accuracy and the limiting lengths of offset. Before you start measuring, you need to decide how precise you need to be. This precision depends mainly on the scale of your survey. Generally, you want to keep the limit of precision in plotting to about 0.25 mm. How accurately you take your offset will depend on their length and how important the details are. Let us see an example, that is, determine the accuracy required in laying down perpendicular offsets for preparing a plan on scale 1 cm to 2 meter. So the solution goes like this. The conversion is 1 cm on the paper equals 2 meter on the ground. So 10 mm on the paper will be 200 cm on the ground. Therefore, 0.25 mm on the paper will be 5 cm on the ground. This means your offset should be measured with an accuracy of 5 centimeter. Now, the allowable length of your offset is an arbitrary. It depends on the few key factors, that is, the accuracy decide how precise do you need to be. Like more accuracy means shorter offsets. Next, the scale of the plotting. Third, the maximum errors in the direction. And the fourth, the nature of the ground. So, the understanding here is, before you head out to the field, figure out how precise your measurements need to be based on the scale of your survey. Working with a scale of 1 centimeter to 2 meter, aim for an accuracy of 5 centimeter. Always consider the factors that affect the allowable length of your offsets to ensure your survey is as accurate as possible. Next topic here for you is the tape correction. So, when you are doing measurements with tape, you want to get things as accurate as possible, isn't it? But tapes aren't always perfect. Depending on how precise you need to be, you might have to make some corrections to the distance you measure. Now, instead of correcting every single tape length, there is another approach. You just measure everything using the tape, write down the measurements, and then later on you make any necessary corrections to the total distance. Next, the correction of standard length. One big source of error comes from something called the correction of the standard length. Here is what that means. Before you even start using your tape, the actual length is ascertained by comparing it with the standard tape of known length. If the actual tape length is not equal to the standard value, a correction will have to be applied to the measured length of the line, which is given as CA is equal to LC by small l, where C is a correction for absolute length and capital C is a correction to be applied to the tape, L is the measured length of the line and small l is the nominal length of the tape. The sign of the correction CA here will be same as that of the C. Next, we have correction for slope. When you are measuring along a slope, the distance you get is always going to be a bit longer than it you measured the same thing on flat horizontal ground. Think of it like this. Imagine you are walking up a hill. The path you take up the slope is longer than if you just walked straight across on flat ground between the same 2 points. So, if you have measured a distance on slope, you just leave it at that. You have got to immediately convert into the corresponding horizontal distance. This is important because the horizontal distance is what you really need for accurate mapping and calculation. The slope's correction is given as CSL is equal to h square by 2L. H is the distance in elevation of A and B, L is measured length and the slope correction is always subtractive. Correction for tension, that is pull. Again, when you are out for measuring and if you pull on the tape harder than you are supposed to, that is harder than the standard pull that the tape was designed for, the tape actually stretches a bit. And here the catch is, when the tape stretches, the measurements you take end up being a little off. Specifically, the distance you measure will be shorter than it really is. It is like if you were to tug on a rubber band, it stretches out, right? The same thing happens with your tape. It throws off your measurement. So, if you are not careful and pull too hard, you might think you have measured accurately, but your final numbers will be slightly less than that it should be. So, the pull correction is given by Cp is equal to capital P minus P naught by AE into L, where P naught is a standard pull P and E is the area of the cross section of the tape and E is a module of elasticity of tape, that is 2.1 into 10 power 5 Newton per mm square for steel and 1.54 into 10 power 5 Newton per mm square for N bar, and L is a measured length in meter. So, tension correction is positive if the applied pull is more than the standard pull and negative if the applied pull is less than the standard pull. Next, we have correction for temperature. The length of your tape isn't always constant. It actually changes with the temperature. So, to deal with, you have got to make a temperature correction usually called CT. It is a simple fix that adjusts your measured distance to account for the tape expanding or contracting due to the temperature at the time you measured. Ct is equal to alpha into Tm minus T naught into L, where Tm is the mean temperature during measurement and T naught is the temperature of standardization, and alpha is the coefficient of thermal expansion of the material, which is 0.000035 per degree centigrade for steel and 0.60122 per degree centigrade for N bar, and L is the measured length in meter. The correction is positive if the temperature during measurement is more than the standard temperature, and negative if the temperature during measurement is less than the temperature at which the tape was standardized. Next, we have sag correction. When you stretch a tape between 2 points, especially over a long distance, it does not stay perfectly straight. Instead, it sags in the middle and form a shape called catenary. So, to fix this, you need to apply what is called sag correction or CSA. This correction adjusts from that extra length caused by the tape sagging. So, your final measurement is accurate, and it is given by these formulas. Cs is equal to neta W L1 the whole square into L1 by 24 P square is equal to WL by N the whole square N L1 by 24 P square. Equating it, we can arrive at the value CS1 is equal to W square L by 24 N square P square, where W is the weight of the tape per unit length and W is the total weight of the tape and P is the pull applied in Newton, and L1 is the length of the tape suspended between two support and L is the length of the tape, and sag correction is always negative. Next comes the reduction to the mean sea level. When you measure a line at higher altitude like up in the mountains, that distance is actually a bit longer than if you measure the same line at the sea level. This is where the altitude correction, usually called CR, comes in. It adjusts your measured distance to what it would be if it were measured right at the mean sea level, making sure everything is consistent when connecting to the national grid or any other standard reference system. So, CR is equal to small h by r into L, where r is the radius of the earth, and this correction is always subtractive. Let us walk through an example. A 100-meter tape is suspended between the ends under a pull of 200 Newton. The weight of the tape is 30 Newton. Find the correct distance between the tape ends. Solution goes like this. The correction for the sag, CSA is equal to W square L1 by 24 P square. W is given, that is 30, L1 is given 100 and 24 into 200 square, which comes out as 0.09375. From which the horizontal distance is equal to 100 minus 0.09375 is equal to 99.90625 meter. In today's lecture, we discussed chain surveying, a fundamental land surveying method where the sides of various triangles are directly measured in fields without any angular measurements. We covered its purpose, including defining boundaries, determining areas and preparing accurate land plans, and identified when chain surveying is most suitable or unsuitable. We explored the principle of dividing an area into triangles, emphasizing the importance of well-conditioned triangles, and learned about the technical terms and definitions such as main survey station, baselines and check lines. We also reviewed the selection and measurement of station and baselines and the methods of measuring offsets, both perpendicular and oblique, along with their degree of accuracy. Finally, we looked into the tape correction and an example problem associated with it. This comprehensive overview highlighted the significance of precise measurement and strategic station placement in achieving accurate land survey. Happy learning. Good day.